Okay, a very good morning to you all. My voice is audible, I think. Is it audible?
Yes, ma'am.
Okay. Okay. So from next week you have your exam. So let me cover up some topics of module 3 today. Okay. So I'm sharing, I think most of given your QR code, I'm sharing a screen with you. This picture is visible to everyone, I think. See, in previous class, I have discussed with you signal generator, but a very simple diagram. Remember, if you follow my previous lecture video, which is uploaded in YouTube, you might find that there I have used a very simple diagram, okay, to make you understand about this signal generator. Even I told you that I will show you in the next class the basic diagram of a laboratory type signal generator. So this is basically laboratory type signal generator, right? Okay, so you can find this circuit a bit complex one, and some advanced type of devices are used here also. So this a master oscillator has been used here. Okay, this master oscillator actually this is used, which is optimally designed for highest frequency range. Okay, and RF oscillator you can see here, there is a particular frequency has been given here for RF oscillator. So RF oscillator, the output filter, RF oscillator, the output filter that is passing through an untuned buffer amplifier. So buffer amplifier means, see, you see here this output of this RF oscillator, here a B1 is connected. So this is the buffer amplifier actually. Okay, this B1 is the buffer amplifier. Buffer amplifier. Now this B1 enters the power amplifier circuit. So this is the power amplifier assembly. This whole thing is the power amplifier assembly. Okay. So on the highest frequency range, which is written here in the RF oscillator, that is 34 megahertz to 80 megahertz. This is important. Okay. 34 megahertz to 80 megahertz. This is the highest frequency range. The RF output then passes to an additional another. So one buffer amplifier is B1, second buffer amplifier is B2. Okay. So in order to obtain the low frequencies, the RF signal is applied to a series of frequency dividers. So see here, you can see the frequency dividers, which is having at least 9 frequency, and it's a 2:1 ratio. Have you see here? All these, and here see another buffer amplifier is connected. So the frequency ratio of 2:1 that we can obtain in a various ways. Okay, so you can see here the frequency dividers provided is in 2:1 ratio. Okay, so the on the lowest frequency range we get an output of what output we can get. You see here, it's not written here. I'm telling you whatever output we will get, that will be in the range of 67 kilohertz. Okay, so kilohertz to 156 kilohertz. This is my output. This is my output range, 67 kilohertz to 156 kilohertz. The frequency stability of highest frequency range is then imparted to the lower frequency ranges. Okay, now the master oscillator, which I told you, this master oscillator have both you can say automatic and manual controllers. Okay, and what else with these controls which are given here? You can see whatever controls are being given here. With the help of their automatic tuning actually happen, and the modulation is done at the power amplifier stage here. Okay, and for modulation, two internally generated signals are used here, and which have a frequency of this one, 400 to 1000 kilohertz, 400 hertz to 1000 hertz, or I can say it's 400 hertz to 1 kilohertz. Okay, so this is my two internally generated signals which is obtained from this. And the modulation level here adjusted up to 95% with the help of the controlling device. Now the signal generator here provided with a what? With a 1 megahertz, crystal oscillator. With a 1 megahertz crystal oscillator. So this signal generator actually consists of this thing, this 1 megahertz crystal oscillator for calibration purpose. Okay, so this is all about the standard signal generator. So just have an idea, especially in previous class, the video which I uploaded with a simple diagram, that is more effective. This is okay. This is for better understanding that how in lab signal generator looks like and what are the what are the input outputs are going, what the frequency range changing, that may help you. Okay. So this is the signal generator done. Now next we will move on to square wave generator, which is in your syllabus. So I'm sharing my whiteboard and here I'm writing. Acha, the videos which I upload now, so kindly go through the videos. That will help you a lot, because every time what happened in the class, we are not able to concentrate or listen properly. Nahi hota hai. So for that reason, try to go through those videos. I don't find you watch those videos because itna views hota hi nahi hai videos mein. Okay. So I don't think you people even bother to watch those videos, but I think rather reading the book and the notes, if you listen something now, that will always remain in your mind. I believe that. Even I also tried this therapy many times. मुझे पढ़ने से ज्यादा सुनने में I think that always keep in my mind for a long time. So we upload the video for your sake, because sometime before even you people asked to do that. So we do it regularly basis. I mean, each and every day's class is being uploaded by all the faculties in the YouTube. So I don't think you people even bother to watch that, but it's a request to watch those videos, not single time, many times. Your topics will get clear. You can have a clear-cut idea about it. Okay, that is 100 times better than reading any notes or something. Yes, books definitely they are working as a reference, I know, but still. Okay. Okay, so next we have our next topic. This is square wave generator, important topic. So in square wave generator, mainly we have two types of circuit. Okay, so two types of circuit which are used in square wave generator are passive and active. Okay, one is passive and one is active. So what is passive shape of wave or active shape of wave? So passive based circuits actually incorporate wave shaping devices. Okay, they incorporate wave shaping devices, and active in this circuits actually generate square wave shape. So understood? Passive actually incorporate wave shaping devices, and active they actually generate okay, they generate the square wave shape. Now passive square wave generators, they again having various types. So let me tell you that. So next we have passive. We will have just a basic idea. Okay, not so much we will enter into it. Passive square wave generator. So what is passive square wave generator? Now passive square wave generator, any production of square waves can be conveniently obtained from the output of a sine wave generator. Okay, remember this thing very nicely. Therefore, what happens? Both sine as well as square wave output are made available in any commercial instrument. That we will see soon. So oscillator generator, they generates a sine wave output. Okay, and the sine wave may be shaped by square wave by many methods. So there are three important methods by which this shaping can be done. One is diode clipping circuit. So clipping clamping, maybe in basic electronics you have done. You are familiar with this word, diode clipping circuit. Okay, this is number one. Second is overdriven amplifier. And third one is Schmitt trigger. Okay. So these three are the three important methods by which this generator generates a sine wave output. So diode clipping circuit, in case of diode clipping circuit, I'll show you that how this is happening. Wait. Just a second, okay? Let me show you the diagram. Stop sharing here, just a second. Two minutes. Give me just 2 minutes. Okay. Now see, I'm sharing a slide with you, PowerPoint presentation slide. Just have a look. I think this picture is visible to you all. So this picture is actually basically a diode clipping circuit. Okay, this is basically a diode clipping. This is visible now. These circuits are visible to everyone. So this is actually diode clipping circuit. Okay, so simply you see here written at the downward of this picture that simple diode clipping circuit for square wave generation. Now you can see here a simple diode clipping circuit is mainly used for one thing you remember, low level outputs. Okay, when you require low level output, then this kind of diode clipping circuits are important. So diode clipping circuit, they produces an approximate square wave by shaping an input sine wave. So you see here the input voltage is simply a sine wave. Can you see? The input wave is simply a sine wave, right? So whatever output we are getting, there only some picture of square wave you can see. So in order to produce a single peak amplitude of, say, you say here 6 volts. See here, the amplitude of the sine wave is somehow 18 volt, isn't it? 18 volt. But when we are getting sine plus square wave, the square wave is having an amplitude of 6 volt. You can see here. So we are getting this peak amplitude of 6 volt by using ordinary diode D1, which is shown in this figure, right? You can see here two diodes are connected. One is 6 volt battery, another is also 6 volt battery, right? Two diodes are connected with the direction different, okay? And batteries are also connected in different directions. So input is a simple sine wave, which is having 1000 hertz, and its total peak is 36 volt, means 1880. Okay, but when we are getting the output, that is somehow the square wave is having the amplitude of only 6 volt. Okay, so in this particular figure, a biasing battery is used. So this kind of batteries are called biasing battery, so that the input sine wave rises sinusoidally to a 6 volt, okay, value before the diode could prevent further rise of the wave in forward direction during the positive half cycle. तो देखो यहाँ पे जो भी हमारा output हो रहा है, sine wave we are not getting, I mean not so much prominent, okay. Whatever we are getting a square wave. Here also picture has been shown for a square wave how we are getting the output, and because of this presence of the diode it is happening. So similar diode, a D2 is also there, right? So D2 diode and the 6 volt biasing battery is again connected with the Z2 diode for performing the same function during the negative half cycle. Okay, so this is a very basic thing. I mean, in diode clipping circuit, how we are getting the square wave square wave, how we can obtain square wave using sine wave. So this is the actual concept, that how it is when we are using two diode, we are using two biasing battery. So all these are happening here. Okay, so next we will move on to another part was there that was using Zener, but we will not do that. We will then move on to overdriven amplifier circuit. Okay, Achha, wait for a second. Let me show you the picture of this. Wait. Just a second. We will move on to next overdriven. Okay, wait. Overdriven, let me show you the picture. This overdriven is clear, is visible to you all, because I told you this square wave generator have three mainly methods, right? One is first is diode clipping circuit. The second is overdriven amplifier circuit. So this is overdriven amplifier circuit. Okay. So here what you can see, the output is same, right? Means input is a sine wave and output is a square wave. So this thing is same, only the circuits are different. Previously was a direct clipping circuit. So here you see the use of this overdriven amplifier gives a square wave of greater amplitude. Okay, and the amplifier is overdriven by a sine wave of desired frequency. So let us see the circuit for an overdriven amplifier is this one. As you can see, now circuit here uses a series grid resistor. That is this RS. This RS is called series grid resistor. Series grid resistor. Okay. And a low grid bias. Low grid bias is also there. The output corresponding to the positive half cycle is flattened almost completely by the flow of the grid current. Okay, so for the negative half cycle, the sine wave, the output becomes again flattened as soon as the cutoff point is reached. So in this particular figure, you can clearly see that using this particular overdriven amplifier circuit, this is my input sine wave. Okay, this is my input sine wave, and the output what I'm getting is a square wave. Okay, is a square wave output voltage. It's written clearly square wave output voltage. So the resulting wave shape is similar appearing obtained in the from the diode clipping circuit, but here the amplitude is high. You can see that yes, in the previous circuit also we are getting the same square wave output voltage, but in special cases that here the amplitude, whatever output voltage we are getting, that amplitude is high. Okay, amplitude is high. So this is the basic difference in between the diode clipping circuit and your this one, diode clipping circuit, and this overdriven amplifier circuit. Now we will move to next, that is schemic trigger circuit. So let me show you the schemic trigger. Wait. Just a second, let me take the diagram of schemic trigger. I'm sharing now the picture of schemic trigger. This is the picture of schemic trigger circuit. I think it's visible to everyone. Visible?
Yes, ma'am.
Okay. This is schemic trigger circuit. So 3 circuit I told I will discuss in case of square wave generator. So one I told you direct clipping, second is overdriven, third is schemic trigger. So you see here, this figure actually typically shows the schemic trigger circuit, and there are possibly 2 outputs from this circuit, level 1, level 2. You see here, UTP, LTP, 2 levels are given, right? UTP, LTP. देखो यहाँ पे लिखा हुआ है. So mainly we are getting 2 possible outputs from this circuit. Okay, how? Actually, that is level 1. If you say which occur from transistor from which occurs when the transistor Q2 is turned off. See in this particular picture, there are 2 transistors. There is Q1, here is Q2. Okay, so one waveform is obtained, that is level 1. If I say level 1 waveform is obtained when your Q2 is turned off. Okay, or you can say Q1 is on and Q2 is off. Okay, this is how when this happens, level 1 waveform is obtained. And level 0, which one we are saying, level 0, that I'm telling you, level 0 waveform occurs when Q1 is off and Q2 is on. So this is the working principle, how it's going on. So the one level is approximately which one? The one level is approximately here this one, this V00. Okay, this is actually VO. It's not properly printed. ये वाला जो है ना, this is actually level 1. This is actually level 1. Okay, one output voltage. And the 0 level is only V0. That is V0 means you can say which is a combination of the voltage at the emitter and one is a saturated voltage. So that will be actually VE plus VCE. What is VE? V is the definitely the emitter voltage and VC is collector emitter. Okay, because we are using a transistor. So if this is level 1, this one will be level 0. Okay, another one will be level 0. Level 0. So see, upper and the lower tip points on the input signal determine the width of the pulses. So from here we can understand. Achha, another one you see in this particular picture, resistances are 2 resistances are used. Not 2 here. I can see R1, R2, RE, then RC2, RC1, and RB. All the resistances are used. So one more thing, keep in your mind with the resistance, this RC1 is made large. Okay, this one is made large as compared to RC2. Okay, so this is large as compared to RC2, which actually ensures that the voltage, that is VE voltage is obtained, should be twice as high, twice as high with the Q2 conducting than it with the Q1 conducting. So Q1 and Q2 can't conduct simultaneously. Okay, they have to conduct alternatively. So if Q2 is turned on, then what will happen? The voltage which is developed across this RE, that will help in ensuring that the Q1 remain turned off. Okay, this thing actually happens. So remember one thing, when Q2 is turned on, then there is a voltage, that is VE, which is developed across RE, okay, across this RE, help to ensure that Q1 remains turned off. Again, in order to turn Q1 on and Q2 turned off, then what will happen? The input on the base of the Q1 that must rise to a level of that should be greater than the voltage VE. Okay, so this kind of levels which are obtained is called upper triggering level. This UTP is written here, or you can say upper triggering point, upper trip point, anything you can say. So this kind of figures we can obtain because we have 2 transistors here. Okay, so this is an important point. So just have an idea that how direct clipping circuit function, what is the output, how the overdriven circuit function, what is the output, and how the schemic trigger circuit function, what is the output. So try to visualize this diagram. Okay, so then this will help you a lot. Okay, Now, next we will move on to, let me see, the function generators you have or not. Wait. So square wave generators, sorry, next we have actually function generator. Okay, so Schmitt trigger is done. Next we have function generator. Okay, wait. One picture I'm sharing with you. Have a look. Okay, see, in case of function generator, if we come, function generator. Okay, if I talk about function generator, then what will happen? Function generator, as the name implies, it generates specific types of waveform or periodic functions such as sine, square, triangular, sawtooth wave. Okay, whenever in communication, mainly if you learn, many times you will find the application of function generator, because there we need the waveforms like sine, square, triangular, this kind of waveform. So phase locked function generator may be used to produce any kind of waveform. Okay, so function generator, this figure which I have shown here, so this shows actually the typical picture of the function generator. Now this instrument delivers sine, triangular, square wave shapes and typical frequency range here ranging from 0.01 hertz to 100 kilohertz. Okay, so this is the typical frequency range, and signal generator is provided with frequency control network. Okay, and the frequency control voltage regulates here two current sources. So just two current sources means, see here you have two current sources, upper constant current source, lower constant current source. Okay, so for generation of a triangular wave shape, suppose as you see here, three types of amplifier are connected at the output. One is giving square wave, one is giving triangular, one is giving sine wave. You can see now. So for generation of suppose triangular wave shape, an integrator circuit is used. Okay, so you see here, integrator circuit is this one. This is the integrator circuit. This is used actually, and the upper current source here supplies a constant current, this one, and therefore the output voltage of the integrator that can be obtained here, that will be somehow like this: E0 equal to something 1 upon C integration of IDT, it will obtain, and you can find from here I upon C T. So since here obviously the I is constant, the current is constant, it's clearly visible that the output voltage it's increasing linearly with time. Okay, so here the voltage comparator, many voltage comparator vibrator is been used. Have you seen here? ES1. The voltage comparator vibrator has been used here. It is mainly used to change the state at a predetermined level on the positive slope of any output voltage, or you can say integrated output voltage. Okay, so this actually cut off the upper current supply. Okay, and switches the lower current supply. Now see, two current supply cannot work simultaneously. Okay, एक को चलाना है, दूसरे को बंद भी करना है. So we cannot initiate two current sources in the same time. So since direction of the current supply from the lower source is in opposite direction, you see here, these two are in the opposite direction. So what happened? Output voltages, it increases linearly with time. Till the change of the, till that something big changes occur. So however we get this kind of triangular shape. So I have told you that how we are getting triangular wave shape. Now you can see here, with the help of this function generator, we can obtain square, we can obtain triangle, we can obtain sine also. So we have to take into consideration that mainly the slope of the curve which are obtained by this magnitude of the current and the frequency So that actually gives the triangular waveform, which is obtained at the output of the integrator. Similarly, a square waveform can be also obtained at the output of the multi-vibrator. So where is the multi-vibrator? This one. Okay, so in the output of the multi-vibrator, we can obtain a square wave. And the third waveform, which is obtained here, when the triangular waveform is synthesized with a sinusoidal waveform, that is this one. Okay, you see here, a resistance diode shaping circuit has been connected with this triangular waveform. So the third waveform is the sine waveform, and output of the amplifier mainly are used to amplify the signal. So here, the third waveform is mainly obtained when the triangular waveform is synthesized with the sinusoidal waveform. Okay, so this is all about function generator. Very easy. Just try to remember the range in which function generator works. What is the output we are having in function generator, and how these three types of waveforms can be obtained from using function generator. This much will do. This much will help you even if you go through any book. This much is only given. Okay. Now, the next topic we can go with in this particular chapter is the wave analyzer. Okay, for wave analyzer, let me show you one thing. Again, we will be having a wave analyzer. Wait. Not any. Yes. Hello.
Ma'am, can you please share the previous diagram?
Wait. Just a
Function
second.
generator.
Wait, just a second. Just a second, okay? This is the picture of function generator.
Ma'am, already you told that the integrator output is shown as the triangular wave.
Yes. सिर्फ triangular नहीं होता है. Output of the function generator can be a square wave, can be a triangular wave, can be a sine wave. Three types of wave we can obtain from function generator. Okay. But yes, suppose this multi-vibrator, voltage comparator multi-vibrator we require to obtain a square wave. Integrator we require to obtain triangular wave. And integrator with resistance diode shaping current we require to obtain sine wave. Okay. So in the output, we need different device. Our basic is a function generator, but output में जब हमें अलग-अलग waveforms चाहिए, we have to use this kind of device to obtain. Okay, it's not possible that voltage comparator vibrator के help से ही हमें triangular waveform मिल जाएगा. No, we can obtain only square wave from this voltage comparator multi-vibrator. Okay, then we need an integrator only to obtain triangular wave, and integrator with resistance diode shaping current to obtain sine wave. ठीक है? Is it okay, Rajkumar?
मैम ये पूछ रहे थे कि इंटीग्रेटर का आउटपुट तो वोल्टेज कंपैरेटर मल्टीवाइब्रेटर से कनेक्टेड है, एंड हाउ इट जनरेट.
तो इंटीग्रेटर का आउटपुट तो यहाँ पे भी कनेक्टेड है. दिस इंटीग्रेटर इज हियर. सो यहाँ पे भी कनेक्टेड है, यहाँ पे भी कनेक्टेड है, यहाँ पे भी कनेक्टेड है. Integrator output is required everywhere in all the three waves. That is a common output which is required. Understood? Integrator का जो output है वो तो तीनों में ही चाहिए. एक्स्ट्रा एक डिवाइस चाहिए स्क्वायर में जो कि मल्टी वाइब्रेटर है, और साइन में चाहिए रेजिस्टेंस डायोड शेपिंग. दैट्स इट. अदरवाइज वी नीड integrated output in all the three of them. Understood? Hello?
Yes, ma'am.
Okay. Okay, I am now showing the wave analyzer. Wait, what I told, wave analyzer, right? So I was Let me just show you the wave analyzer first. The picture which I have. Actually, wave analyzer, it doesn't have any specific diagram for particular wave analyzer. The types of wave analyzer can show you. This is the actually, I think this slide is visible. So the picture which I'm now showing you, this is specific wave analyzer. But first of all, you need to know what is wave analyzer. That is important. Okay, what is wave analyzer? This is important. So see, wave analyzer is an instrument which is designed to measure relative amplitudes of single frequency component in a complex waveform. Okay. Basically, the instrument acts as a frequency selective voltmeter, which is tuned to a frequency of one signal while rejecting other components. So desired frequency, which is selected, is calibrated using this instrument, and amplitude here indicate either by a suitable voltmeter or CRO. And these are the two types: resonant wave analyzer, heterodyne wave analyzer. Okay, this we will discuss in the next class. But in next week you have exam, so give your exam nicely. We will, syllabus is up to this. Whatever function generator up to this I have learned, only up to this. Wave analyzer nahi aayega up to function generator. Okay, so learn up to this. Please go through the videos nicely. That will help you a lot. And if it's possible, I will give you some notes on this module 3 by today. Okay, so don't worry about it. You will give good exam.